Dear learners, after today's discussion, you would be able to understand the importance and functioning of standard hydrogen electrode, understand the dependence of EMF on concentration of electrolyte and temperature, apply the Nernst equation in calculating the EMF of an electrochemical cell, derive the relation between standard electrode potential of the cell, standard Gibbs energy of cell reaction and its equilibrium constant. From the previous discussion on electrochemical cells, we know a galvanic cell is also referred as a voltaic cell. The electrodes are fixed as zinc electrode and a copper electrode. It is referred to as a Daniell cell. We also discussed electrode potential, which is the potential difference developed between the metal electrode and its ions present in the solution at equilibrium. The potential difference between the two electrodes of a galvanic cell is called the cell potential and is measured in volts. It is called the standard cell electromotive force of the cell when no current is drawn through the cell, or the circuit is open and when standard conditions of temperature and pressure are considered. According to IUPAC convention, standard reduction potentials are now called standard electrode potentials. But we cannot experimentally measure the standard electrode potential of an electrode when it is in contact with its electrolyte in a half cell individually. This is due to two reasons. A half cell, whether oxidation or reduction half cell, cannot work on its own until and unless it is connected with another half cell. The tendency of an electrode to release or accept electrons is only relative and not absolute. This means that it can be only calculated when it is in reference to another electrode. This problem can be resolved by using a reference electrode such as standard hydrogen electrode. A standard hydrogen electrode consists of a platinum wire which is sealed in a glass tube and is connected with platinum foil at the end. This foil is coated with finely divided platinum powder called platinum black. The glass tube along with the wire is dipped in an aqueous solution of 1 molar hydrochloric acid. Hydrogen gas under standard conditions of temperature 298 Kelvin and pressure 1 atmosphere is constantly bubbled through the top of the glass tube. Why do we need such kind of setup for establishing a reference electrode? It is because platinum is chemically inert. Platinum is a good conductor of electricity. The platinum foil is coated with platinum black to increase the surface area for more adsorption of hydrogen gas. The stream of hydrogen gas keeps the solution saturated at the electrode sites with respect to the gas. 1 molar hydrochloric acid solution is taken which is monobasic in nature to get 1 molar concentration of hydrogen ions. Temperature of 298 Kelvin and pressure of 1 atmosphere is taken to maintain the standard conditions. A standard hydrogen electrode is chosen as a reference electrode as it is very special in its working. It can act both as anode and cathode. At the anode, oxidation occurs and the hydrogen gas molecules convert to hydrogen ions. At the cathode, reduction occurs and hydrogen ions gain the electrons lost during the process of oxidation. It is because of this reason that standard hydrogen electrode is called reversible electrode, as it can act as an anode as well as a cathode. A standard hydrogen electrode is represented as platinum, hydrogen gas at 1 bar, hydrogen ions with the concentration of 1 molar, and the standard oxidation and reduction potential is arbitrarily taken as 0. Let us find how to calculate standard electrode potential of an unknown electrode. Now that we know that standard hydrogen electrode acts as the reference electrode, it can now be used along with another electrode to construct an electrochemical cell. And this way, the electrode potential of the unknown electrode can be measured. We may use this process to relate to the galvanic cell as discussed in the previous session. If we connect the standard hydrogen electrode to copper electrode in the circuit, E0 cell gives the value for the standard electrode potential of the half cell, corresponding to the reaction when copper ions gain 2 electrons to form copper metal. The measured standard EMF of the cell is recorded as 0.34 volt using the expression E0 cell is equal to E0 right minus E0 left. The positive value of the standard electrode potential in this case indicates that the copper ions get reduced more easily than hydrogen ions. So in this case, hydrogen electrode acts as anode and copper electrode acts as cathode. Similarly, if we connect the standard hydrogen electrode to zinc electrode in the circuit, zinc gets more easily oxidized than the hydrogen molecules. In this case, zinc electrode acts as the anode and the hydrogen electrode acts as the cathode. Thus, the measured standard EMF of the cell is minus 0.76 volt, which corresponds to the standard electrode potential of the half cell when zinc gains 2 electrons to form zinc. We have learnt that the electrode potentials of the unknown electrode can be measured with the help of standard hydrogen electrode at standard conditions. This way, we will be able to get the electrochemical series on arranging the values of standard reduction potentials in decreasing order. The electrochemical series helps to know whether the electrode will be oxidized or reduced, as the electrode which has low electrode potential has a tendency to get oxidized, and the electrode which has high electrode potential has a tendency to get reduced. To decide the anode and cathode in a cell, to calculate the EMF of a voltaic cell, to predict if a redox reaction will be spontaneous or not, and to predict if the metal reacts with acid to release hydrogen gas. But we also need to know to find a way to calculate the electrode potential when the concentration of electrolyte is not 1 molar. If the concentration is not 1 molar, EMF of the cell is denoted with E cell, which is equal to E cathode minus E anode. Or we can also say E cell is equal to E right minus E left. Under these conditions, the electrode potential and the EMF of the cell can be calculated with the help of Nernst equation. Let us consider the reaction taking place in galvanic cell. Let us first write the two half cell reactions and add them. Zinc undergoing oxidation by losing 2 electrons and copper ions undergoing reduction by gaining 2 electrons. So the Nernst equation can be represented as at anode cell potential for reduction of copper is equal to standard reduction potential for copper ions minus RT upon NF natural log concentration of copper upon concentration of copper ions. We can substitute natural log with the log to base 10 term, and so we get the expression as cell potential for reduction of copper is equal to standard reduction potential for copper ions minus 2.303 RT upon NF log concentration of copper upon concentration of copper ions. Since the concentration of copper is taken as 1, we can simplify the expression now as cell potential for reduction of copper is equal to standard reduction potential for copper minus 2.303 RT upon NF log 1 upon concentration of copper ions. Similarly, cell potential for oxidation of zinc is equal to standard reduction potential for zinc minus 2.303 RT upon NF log 1 upon concentration of zinc ions. To calculate the EMF, we need to take the difference of the two half cell reactions, applying the formula as E cell is equal to E right minus E left. And we get E cell is equal to E naught cell minus 2.303 RT upon NF log concentration of zinc ions upon concentration of copper ions, where E cell is equal to electrode potential under given conditions, E naught cell is equal to electrode potential under standard conditions, R is gas constant which is taken as 8.314 joule per Kelvin per mole. Temperature is T which is measured in Kelvin. N is number of electron lost or gained in the reaction. F is the Faraday constant which is taken as 96500 coulomb per mole. On substituting the values of R, T and F, we can simplify the expression as EMF is equal to E cell is equal to E naught cell minus 0.059 upon N log concentration of zinc ions upon concentration of copper ions. Let us take another example of magnesium and silver electrode. We shall first write the cell through the half cell redox reaction. Left half cell represents the oxidation reaction when magnesium loses 2 electrons, while the right half cell represents the reduction reaction when silver ions gain the electrons. Equating the two half cells, we get the reaction as magnesium plus 2 silver ions gives magnesium ions plus 2 silver. According to Nernst equation now, we may write the equation as EMF is equal to E cell is equal to E naught cell minus 0.059 upon N log concentration of magnesium ions upon concentration of silver ions to the power 2. E naught cell is equal to 3.17 volt, which is calculated after taking the values from the electrochemical series. The number of electrons changed, that is N, is equal to 2 from the reaction, and hence EMF of the cell can be calculated once the concentration of magnesium ions and silver ions are substituted. The EMF of the cell can be used to calculate the value of equilibrium constant in a cell reaction in the state of equilibrium. Once the cell attains equilibrium, it means that the value of E cell is equal to 0, which means that the voltmeter will not show any deflection. In this situation, E naught cell becomes equal to 2.303 RT upon NF log concentration at the anode upon concentration at the cathode, and this can be simplified as 2.303 RT upon NF log Kc, where Kc is the equilibrium constant. This way, we will be able to calculate the equilibrium constant. An electrochemical cell is a source of electrical energy, which can be employed for different kinds of work. The electrical energy is equal to the product of standard EMF of the cell and electric charge flowing through the cell. According to this, the electrical energy is measured as standard Gibbs energy, and so delta G naught is equal to minus NF E naught cell. If we substitute the values of E naught cell found above, we can get the value as minus NF into 2.303 RT upon NF log Kc, and so delta G naught becomes equal to minus 2.303 RT log Kc. To summarize today's discussion, we start with standard hydrogen electrode, which is a special reference electrode. We studied the construction, working and special characteristics of standard hydrogen electrode. We also learnt the way to calculate the electrode potential of the electrochemical cell using Nernst equation as EMF is equal to E naught cell is equal to E naught cell minus 0.059 upon N log concentration of ions at the anode upon concentration of the ions at the cathode, and then correlating this equation with equilibrium constant, as E naught cell is equal to 2.303 RT upon NF log Kc, and further extending it to delta G naught is equal to minus 2.303 RT log Kc. I hope you have understood the concepts explained in today's discussion. Before we conclude this discussion, let me leave you with an assignment. You are expected to apply the understanding from today's discussion and solve the two numericals. Represent the given cell using Nernst equation and calculate the EMF of the cell at 298 Kelvin. And the second numerical is to calculate the delta G naught and Kc, that is the equilibrium constant for a galvanic cell whose E naught cell is equal to 1.10 volt. I hope you have understood the concepts explained in today's discussion. Have a nice day.